Are you going to be targeting this list?
All right, welcome back. Hope you guys all had a nice and restful break. Start off with going over the calendar, just to kind of give you an idea what's coming up. If you guys didn't pick up a packet, guys have packets up here next to your phones. So this semester we're talking about anti-derivatives. We're basically taking everything that we learned with derivatives and we're undoing that process. So it's kind of like when you first learned math, you started with addition first, and then you moved on to subtraction, right? So we're undoing this process with derivatives, but we're going to get there. We won't get there until probably after this quiz, but really we're going to see that to undo derivatives, anti-derivatives involves area, and I'll show you that connection between slope and area a little bit later. But really, we're just starting with approximating area under a curve. And we're going to be working with rectangles a lot because rectangles is the easiest area formula. So, but we need some tools first before we can get there. So we really won't get there until tomorrow. So today we're just talking about sigma notation, a tool that we're going to need. We want to add a lot of different rectangles together to make our approximations better and better. Our quiz will be next Friday, but we'll have a couple days to review. I'm hoping that we can get through our topics by the 9th, and we can start our review early. Hopefully, we'll have 2.5 days of class time to review, and then quiz Friday. MLK will be after that, and then we'll work to finish off the rest of Unit 4 by the end of the month. Now, this is a big unit here, so we're gonna have 2 separate test grades for this unit. The first one will be non-calculator, and the second one will just be kind of practicing a lot of the features that we're going to learn on your calculator. So the 36 Pro can do a lot of this, but again, really want you guys to get comfortable with the graphing calculator. So I do have some that you can borrow, but really want you guys to hopefully, if you're able to get a TI-83 or TI-84 in preparation for the AP exam. Okay.
A lot of calculator stuff can be like later on.
Yeah, it's we're gonna have calculator sections from here on out. Yeah, so every test we're going to see some calculator feature that we're going to really need to use.
Okay.
Yeah.
But like when we started, are we mostly non-calculator, or are we just going to go?
Yeah, mostly it's going to be non-calculator first, and then we'll bring in the calculator. Yeah, but yeah, the calculator portion for this unit will be very specific. So very specific skills that we'll practice. So you'll know exactly what to do. There's only a few things really, but the graphing feature is really important. And you're able to do it with the 36 Pro, but it's just a lot more tedious, a lot harder if you're just looking at a table of values. Okay, I'm going to flip through the packet here. So on the inside cover is your calendar. Okay, calendar here on the inside cover. Now this is the first packet, so this will only cover up to the quiz. We're going to go through these pages of notes over the course of this week and next week, and your homework assignments are all going to be contained near the back. So near the back here, starting on page 47, you're going to see, we're going to first start off with 4.2, then we'll go back to 4.1, and all your homework assignments are going to be detailed on your calendar. Okay. Now I'm still trying to figure out how to transition to the new textbook. So Right now, we're still using the old textbook. I just feel more comfortable with it, at least this semester. So I will send out a link to what I want to show you in a second, but just want to kind of point this out to you. So okay, so on my website, we're going to be starting. This is chapter 4 integrals, okay, and I'll send you a link to that. There's a homework solutions Calc chat. So if you click on this, okay, near the top of the page. Right now we're on 4.2. So for any problem that I assigned for you, I'm giving you all the odds. So 4.2, let's say you want to see the solutions for exercise 11. Go just click go, and then it'll show you the solution. So just want to make sure that you know where to look to check your answers for all your homework. And I'll send you a link to this unit page as well as to this Calc chat so that as you're doing your homework, you know where to look to check your answers. Okay. Okay, so let's start off. Page 1. Okay, so sigma notation is, we're going to need this later on when we want to add a lot of areas of rectangles together. So first, this is a sigma notation. And all this means is that this is a symbol to indicate that we want to add a bunch of terms together. Okay, I'm gonna have you guys copy these things down here. First, couple of features around this sigma notation here. There's the index. The index indicates the variable that you're going to be changing over the course of these terms. There's the lower bound. Lower bound indicates the first variable value that you're going to insert into your argument expression, your formula rule, your rule of sequence. A lot of different ways to indicate what that means. So we're adding a bunch of terms together. So 2 is going to be the first value that you insert into the expression. And then you're always going to increment by 1. So if we start at 2, then the next term is going to be a sub 3. And we're going to be adding the terms together. Then the next thing will be a sub 4, then a sub 5, then a sub 6. But we stop at this upper bound value. So this is the first value of I. This is the final value of I. Some students feel like this 5 represents that there are 5 terms. That is true if we always start at 1. But if we're starting at a different number other than 1, then that 5 doesn't necessarily indicate that we always have that many terms. So just want to make sure that we don't. I see a lot of students, they will go to a sub 6 because they think that the 5 means 5 terms, but it just means that this is the last I value that you insert into the expression.
you said about the upper bound, lower bound, like the definitions for.
Yeah, so that's the question. Hold on. So let me demonstrate that in an example, and hopefully that'll make more sense. Okay, but everybody have this copy down. So for instance, example 1 here, it says I equals 2 to 4 of I squared plus 1. I squared plus 1 is my rule of sequence. So what's the first term that I'm going to plug in for I? 2. Yep. So I'm going to plug a 2 in for I. So I get 2 squared plus 1. Okay. All right. That's the result from I equals 2. What's the next I value that I want to insert? 3, right? Yep. So I'm always going to move up by 1. So the next is going to be plus 3. 3 into the entire expression. Okay. What's my next I value? 4, right? So plug 4 in. 4 squared plus 1. Okay. Do I keep going?
No, because that's like the top.
That's the last value. That's right. So here, there's only 3 terms, right? There's 2 squared plus 1. There's 3 squared plus 1. There's 4 squared plus 1. So the 4 doesn't mean that there are 4 separate terms. The 4 just means that's the last I value that you insert into the expression. Okay. And now you're just adding these terms up.
So whatever's on top will be the last.
Whatever on top is the final I value for the expression. Yeah. And you're always going to go up by 1. So you're never going to jump from 2 to 4. And this from 2 to 9, then you got to do plug 2 in, then 3, then 4, then 5, all the way up to 9.
When you get your final answer, you need to like rewrite what's like the original.
No, you just have to, you're just going to get a number.
Oh, just get a number. Okay, so
Yeah.
you don't have to like write sigma.
No. You're just going to get a number. So this is not a difficult concept, but you can imagine how tedious this could be if I'm going from like 2 to 100, right? I mean, having to do all this by hand, that's not something that we're interested in doing. You know, if it's only a few terms, then we can do it by hand. But if it's a very large term, a very large upper bound, then we would like to have some shortcut to be able to move our problem faster, right? Or move through our problem faster. Okay. Any questions? If it's just a few terms, you're just adding a bunch of terms together, and there's a way for you to start, a way for you to end, and a way for you to know what terms you're adding together. Now we have these summation formulas. These summation formulas allow us to have a little bit of a shortcut, but only for these specific scenarios, right? So I want to talk about the first 2. And once you see that first 2, then hopefully you will kind of understand how to interpret the 3rd and 4th and 5th one. So the first one here, summation from 1 to n of 1 is equal to n. So for instance, let me demonstrate how this rule can look. So here's an example. Let's say I want to go from 1 to 5, and my rule of sequence is 1. So what's the first I value that I'm going to plug in? 1, right? Is there an I value here? No. So the only thing I'm going to get from that is what? Just 1, right? Okay, so 1 plus. Now my second I value is 2. What's my term that I'm going to get back in return? Still what? Still 1. Okay. And then 8, and then plug in 3, I get 1. Plug in 4, I get 1. Plug in 5, I get 1. Do I keep going? That's the last one, right? So what's 5 ones added together? Just equal to 5.
How do you just plug in ones again? Sorry, instead of like.
Because this is my rule, right? There is no I in here. So if I plug 1 in here, I'm going to get a 1 in return.
Okay.
Right. So the shortcut is this. The shortcut is, if you notice that this 5 is the same as the upper bound. So whatever the upper bound is, that's going to be your sum, right? Because you're just adding ones together. So if it's from 1 to 10, then adding 10 ones together would just be 10. So that's this rule. The rule just says, if I'm going from 1 to n and my rule of sequence is 1, then my sum is always going to be matching my upper bound. Now let's look at the second rule here. summation from 1 to n of I is equal to n times n plus 1 over 2. Let's just let's again choose 5. And let's do 1 by hand just to kind of see how this rule works. So if I were to go through this process here, what's the first term I get? 1 plus, what's my second term? 2, right? This is now it's changing, right? Because now it's not just a 1, it's going to be changing with whatever this lower bound is. So plus next one, and I keep going until 5. Okay, if I add those values together, what do we get? 15. Now, obviously, that's not difficult to do, but imagine if you're going from 1 to 100, we would prefer to have some sort of rule. And the rule that we can use is this n times n plus 1 over 2. So I want to show you that this formula can work for something that we know to be true. Sorry, say I equals. So what we're going to do is we're going to take the upper bound, insert it for n. Okay. So 5 times what? Was 5 plus 1? 6. So 5 times 6 divided by 2 was 5 times 6. Divided by 2 is same thing, right? So I just want to convince you that this rule does work, but it's very useful if we're going from like 1 to 50 or 1 to 100 or 1 to 200. We don't have to add up any terms. We can just go through this formula, go through a quick calculation, and we can get that sum. And hopefully the third and fourth rule makes sense as well. This would be 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared up until whatever my upper bound is. Rather than adding up all those terms, this formula will get to my sum a lot faster. Okay. This one will be 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed. Now, this fifth rule, all this is saying is to help us see our rule a little better, if I have any coefficient, I can just pull that out in front to help me kind of isolate the parts that that I don't need to worry about for my rule. So for instance, if I had summation of 4i, I can write this out as 4 times summation from 1 to 5 of I. And I can just focus on, okay, let me figure out what this rule is, get this to be a number, and I can multiply by 4. And then that 4 doesn't feel like as if it's messing up my rule. I can just push it out in front and then just kind of separate the parts that is not going to impact my my sequence. Okay, so this is just more of a visual aid so that we can kind of identify the rule easier if we don't have that coefficient that's, you know, making it more difficult to identify. So I can always push that coefficient down in front, figure out this part, and then multiply that by 4 at the end.
Oh, I see you circled like everything but the four still.
I'm sorry?
I see you like when you circle it down there, like you circle everything but the fours.
Oh yeah, so this just for me to indicate that if I can figure out this piece first, I can get this number out. So I can get this to be 15, and 4 times 15 equals 60.
Okay.
Yeah, it just allows me to separate separate my problem a little bit easier. Okay, so example 2. Here, notice that I have 3i squared plus 2. I'm going from 1 to 8. I could add up the terms one by one. It wouldn't take too long, but we're going to practice with the summation formulas that we have in front of us. So anytime I have a separation between two terms, I can treat them like two separate problems. So I'm going to write this out twice. Okay, what can I put this 3 to make it easier for me to see what rule I'm going to apply? Push it out in front, okay? Now I'm also going to push the 2 out in front. Okay, if I push a 2 out in front, what's left in here? Not a 0, but a what? A 1. Yeah, 2 times 1 is 2. But the nice thing about pushing that 2 out is you can see, you can match the rule a little bit easier because we do have a rule for summation 1. Okay, so I'm going to box this off, and I want to show us that we're just going to apply the rule where it applies. And once we convert these two numbers, we can multiply it with the coefficients out in front. So what rule can I use for summation from 1 to 8 of I squared? Yeah, summation I squared, right? Summation I squared is n times n plus 1 times 2n plus 1 divided by 6. What's the n value in this case? 8. That's it, my upper bound. Yep. Okay, so 8 times, what's 8 plus 1? 9. What's 8 times 2 plus 1? 17. Divided by 6. Okay. Okay. You can use your calculator, or you can just wait for me to do this for you. Okay. What rule can I use for summation 1? This one here, right? And summation 1 is just going to be what? Equal to, yep, my upper bound. So all this could just be inserted into your calculator. So it's probably not that big of a deal with only 8 terms. We could have done this by hand, but imagine if it was going up to 50 or 100 or 200. We don't want to painstakingly go through every term one by one. We want to use these formulas. Oh, and by the way, I will give you these formulas on the quiz or test. You're not to memorize them.
They give them to you on the AP exam?
Typically, these show up in yeah, these rules don't you really don't see these rules on the AP exam. It's more like applications of them.
So you
And
apply them.
yeah, so this is more like the basics that will help us get to where we want to be. So we do need knowledge of this to be able to answer some of the AP problems, but you won't see AP problems like this. This is a little bit too basic, but this is still an important foundation for us to build on. Yeah. Okay, example 3. Any questions here with 2? Okay, example 3. We still want to split up into separate terms, but what's different between 2 and 3? Yeah, that squared is not quite, these are connected in more ways than one compared to this one. This one we can separate between 2 terms, but this is really I plus 2 times I plus 2. So we really want to, yeah, you want to resolve the exponent before you can really clearly see the terms that are in play. So before we can do this, you're right. Let's FOIL this out. Let's get everything nicely separated before we decide how we're going to separate them. Okay, so this becomes I squared plus 2i plus 2i plus 4. So now it's a lot more clear, right? I squared plus 4i plus 4. Okay, so now how many summations can we think of this as? 3 separate ones, right? Let's just divide and conquer, right? So we'll kind of think of these as 3 separate problems. We'll solve each individual sum, and then we can add it all together. Rather than think of, it's a lot easier to think of it as 3 smaller problems than 1 larger one. So, and then as I separate them, I'm going to push the coefficients out in front to help me see the rules better. Okay, you guys want to try this one here? See if you can figure out which rule to use and how to use the rules.
Number. Yeah.
All right.
What do you, oh, I think it's which ones?
Yeah, so this one you will use rule number 3,
Number 3.
right? Because it's I squared, right?
Yes.
Okay. And this one you'll use rule number 2. And this one you'll use rule number 1.
Also, different rules for each.
That's right. These are all separate rules, right? There's summation I squared, there's summation 1, sorry, and summation I and summation 1. Okay, so this one, my formula is n times n plus 1 times 2n plus 1 all over 6. This one, summation I is just 10 times 11 divided by 2 with a 4 in front. And the summation 1 is just going to be n, right? So we're just adding all that up using our calculators. What feels more complicated about number 4? Yeah.
The one by n.
Yeah, and also there's like 2 letters, right? There's 2 different, or what looks like variables. But here, the only variable that we have is actually going to be what? What's the variable in this problem? Not the n. It's going to be the k. The k is what's changing, right? The n is going to be some unknown constant, right? So here, k is the variable. So you'll treat k like I. And then your n is a constant or some unknown constant. It could be a 3, it could be a 4. So what that means is by the end of the problem, we still have to have n's in our answer, which is we're not going to be able to resolve n. But instead of instead of I squared, we'll think in terms of k squared. Right? But it's the same idea. We can kind of separate, distribute, and then separate into individual sums. Just distributing, and as I distribute and separate, I'm also converting it or making it into 2 smaller problems. What can I push out in front? Yep, n is the constant, right? Just like before, any coefficients I can push out in front, it's the k that has to, that's part of the rule, right? We'll treat k as I. Right. Oops, sorry. I'm pushing out the 1 over n, not the 1. Okay, I'm going to box off the parts that I'm going to change because of my rule. Whatever's outside is just gonna stay with my answer. So what rule can I use for summation from 1 to n of k squared? Same rule as I squared, right? Just a different index. So, but I don't have an n value, so I'm gonna have to hold on to all my n's. My n will just be in my final answer. And summation 1 can be replaced with what? Just not, yeah, just n. Yeah, summation 1 is just n. Just going to do a little bit of cleanup here. Here my n's can cancel out numerator and denominator, and I can FOIL that top part out. N and n cancels out to be just 1, so that's fine. I can leave it like this. As far as I can go, because I don't know what my n value is. If I knew what my n value was, I'll be able to replace my n with a number and get the sum. But this one is giving that flexibility for find the sum for any n value. We can use this. Okay, page 2. Okay, we're going to bring back limits, but only for limits approaching infinity. So if you think about limits approaching infinity, let's think back about finding horizontal asymptotes, right? If we do limits approaching infinity, what we do is we don't plug in anything, we compare degrees, right? So let me just do a quick example here. Limits as n approaches infinity of 100n squared over 2n squared plus n. What do you think this is? If the degrees are the same, my limit will just be what? Yeah, just my ratio of the coefficients, right? 100 divided by 2. The lower degree doesn't matter. So this is equal to 100 over 2, which is 50. So example 5, it says, if my function is n times n plus 1 over 2n squared, find the limit as n approaches infinity. So let's just put that limit in front of this. Let's clean this up, compare degrees, and then we can decide what my limit is going to be. It's hard to see what the degrees relationship is. So let's just get it all under one fraction and get everything cleaned up. Get the brackets and the parentheses to go away. So I can just have it as one fraction, right? What's my numerator going to be? If I distribute through n squared plus n. My denominator will just be what? 2n squared. Okay, so limit as n approaches infinity. We compare degrees. Are the degrees matching? Yes. So my ratio of the coefficients will just be what? 1/2. Yep. There's a hidden 1 in front. We should take that 1 and 2 and divide it. We get 1 over 2. Any questions? Okay, example 6. We're going to evaluate the limit, but first we're going to resolve this first. We're going to involve our summation rule to get everything in terms of n. Once everything's in terms of n, then we can organize our degrees and see what that limit is going to be. But first things first, we're not going to worry about the limit. We're just going to try to clean that expression up. Okay, remember, n is the constant, I is the variable. So any constant we want to push out in front is not going to be impacted by our summation rule. Okay, let me just combine this together, kind of have a easier way of organizing this. If I multiply all this together, what do I get? 4i over n squared. Okay. Let's separate the parts that is not impacted by the rule and the parts that is impacted by the rule. What can I push out in front that I don't have to, that is not going to change because the rule is not going to impact it? The 4 and the what? And squared. Yeah. So push that on the front. It's the summation I that we really want to isolate because we know that is the rule that we can use from the first page. So this is what I care about changing, right? Okay. What's summation I? Yep. N times, yep, n times n plus 1 over 2. So I'm just making a substitution. Everything in terms of n, so I can have apples and apples to put together and compare, right? So n times n plus 1 over 2. Now I have like variables, and now I can move towards cleaning it up and working the limit into my problem. Okay, so just like before, let's clean everything up, get it all into one fraction so we can clearly see the relationship between my numerator and denominator. Okay, if I distribute that 4 through, the 4n through, what do I get? 4n squared plus what? 4n, yeah. So I'm distributing the 4n through the parentheses here. My denominator is just what? 2n squared. Okay. Should be nice and clean now. What's my limit going to be? 4 over 2. I don't care about my lower degree, right? It's only the highest matching one that I care about. Okay, last one here. This one is the most complicated one because here is what we need to do, right? We have to FOIL all this out, clean all this up, then we'll distribute, then we'll separate into our individual limit terms, push out our coefficients, then we'll decide where the rules are going to apply, get everything in terms of n, then we can evaluate the limit within each fraction. Okay, but we got to spend time to clean all this up, right? We can't just go ahead and separate because this is not ready to separate yet. Things are hidden from that binomial squared there. I'm going to put the 2 over n in front, and then I'm going to try to just eventually work towards cleaning all this up. So we'll write this out twice to help me see that I can't just distribute the 2 through, right? I got to spend time foiling this out. I'll deal with the 2 over n later. I'm going to just focus on foiling out my parentheses there. Combine some like terms there. 2i over n plus 2i over n is what? Let me get rid of all the parentheses. And now I'm going to individualize each term with its own summation and with all the coefficients pulled out in front so I can isolate the parts that the summation rule will impact. Okay, so for my first summation, what can I push out in front? 2 over n, and then what's left over? 1, good. Second term, I can push out the what? And the over n squared. I's left over. Last term, I can push out, yep, 8 over n cubed. Okay, let me box off the parts that I want to convert using my summation rule. Anything in front is just going to hang out until things are ready to combine. Summation 1 gets replaced with not 1, but n, yeah. Summation I is n times n plus 1 divided by 2. Okay, so summation 1 is n. Summation I is n times n plus 1 over 2. Summation I squared is n times n plus 1 times 2n plus 1 all over 6. I'm going to put a limit in front. I'm going to evaluate the limit of each fraction and compare degrees for all of them. Now, there's a bit of a shortcut to this. This feels like a lot to do, and it is, but we only care about what degree? Do we care about all the degrees in the numerator? We only care about the degree with the what? The highest, right? So the way you reach the highest is you just multiply all the first terms together, because that's going to produce the highest degree. Everything else is going to be a lower degree. Any lower degree is it's not going to matter, right? It's going to drop out. So what's 8 times n times n times 2n? 16 n cubed. Now, there are a bunch of other terms, but we can ignore them because they're just going to drop out, right? Just like this 8n, I really don't need this because I know it's going to be 8 over 2 is 4. So all the n squared, n, and constant is not going to matter. It's just the highest term. So now we just compare each fraction. 2n over n, which is going to be what? 2. Degrees match for this fraction. My second term will just be what? 8 over 2, which is 4. And then my third term, I'm doing a bit of a shortcut, right? I don't care about all the other degrees. I just care about the highest degree. Every other term is going to produce a lower degree. So this is just 16 over 6. And that's my limit, right? Add all that together. Okay, guys, your homework If you go to the back of your packet, page 47, 4.2, and then if you look at the inside cover where your calendar is, it'll specify which problems. And I want you guys to do this on a separate sheet of paper. I want you to have plenty of room. So I'll send out a reminder. I'll send out the link to Calc chat so that you guys can check all your answers. Okay, go get your phones.
Anybody ever want my number?
Yeah.
What do you put dots along since it's been?
Guys, there are more terms if I were to call out, but I don't care about those terms because those are lower.
Okay.
I just care about my highest degree because I just want to find a way. All right. Teaching, six months and more. At least it once. 6 months. Thank you.
Yours is from high street.
That's right. Now, within each fraction, you just look for the highest degree. And once you can get that, then now all the problems that I give you, there's always going to be a matching pair. So there's always going to be a 2 and 2, a 3 and 3, or 1 and 1.